Hello everyone, welcome to my channel Hypermesh Basic to Advanced. So to have a bit of a background about this channel, in this channel I make videos related to FEA and Hypermesh. In addition to this channel I also have a website, the link to which I will pin in the description, and just go and check it out. So if you are interested in FEA and Hypermesh, you can just consider subscribing to my channel, as I post regular videos on this channel related to FEA and Hypermesh. Also, if you are a regular viewer and not subscribed, kindly consider subscribing, as it motivates me to further make videos on these topics. Right? Okay. So changing on to the topic of today's video. In today's video, we'll be performing a non-linear contact analysis. Right? So what is non-linear contact analysis? So contact analysis, as the name suggests, we are going to analyze the contact between two components, two subjects, two structures, whatever it is, right? So the word non-linear, right? So what is non-linear? So non-linear refers to the connection, or as in the relation between the input and the output, right? So if the input and the output are related linearly, like if you check the relation, it comes in a linear form, then it's a linear relation, right? And if it's a non-linear relation, it's non-linear, right? Suppose if it's like the output increases in proportion with the input, then it's linear. And if the output changes, like not in the exact proportion, but in terms of square or cube, or maybe might be inversely proportional, something like that, then it's non-linear, right? Okay. So that is what is meant by non-linear contact analysis. Okay. So for this analysis, I already have mesh model, as you can see on the screen, right? For this contact analysis, I have rack and pinion, right? As you can see. So I've meshed the rack and pinion using 3D hex elements. You can see on the screen, right? I'll just zoom in. So you see these are meshed using 3D hex elements, right? So what we are going to analyze in this, the contacts. So where will be the contacts? So as you can see here, there's contact between the rack and the pinion right here, right? When the rack will move on, when the pinion will move on the rack, there's a contact between, right? So, but we are not going to do exactly the same thing. We are going to do something different, right? So in this tutorial, what we will do is we'll just fix the inner face of the pinion, right? As you can see here, I have already fixed the inner face of the pinion, fixed all the degrees of freedom 1, 2, 3, 4, 5, 6. You can see here, right? So I've fixed all the degrees of freedom of the pinion, right? I've fixed this face. So basically, this is fixed. So what we will be moving? So the rack will be moved, right? So if you can see here, I've applied a force here on the rack, right? You can see there's a force of 4,000, right? 4,000. You can just zoom in here. If you see, there's a force of 4,000 Newton applied in the x direction, right? So what we will be doing is we'll be fixing the pinion and we'll be moving the rack, right? So first of all, we have to mesh the components, right? The rack and the pinion, which I have already done using 3D hexagons. Next, we have to apply the load on the bottom face of the rack. So for that, what I've done is I've created RB2 elements and selected the nodes on the bottom face of the rack and applied a force on the master node of the RB2 elements, right? If I go to components here, you can see I have an RB2 element here, okay, and I've applied the force on the master node of the RB2 element, right? Now after that, what we will do, we have to fix the pinion, right? So for that, we can just go to analysis. You can see here analysis. We can go to constraints and we can just go to, I have selected your faces and we can just go and click the face here and it will select all the nodes on the inner face of this pinion, and we just need to check all the degrees of freedom that we want to constrain. So I've checked all the degrees of freedom because we are completely fixing the inner face of the pinion, right? And then we click create and then it will create the constraint, right? So similar way for creating force, we can just go to analysis and we have forces here, right? And select this and we can then select the master node of this RB2 element, and then we can give the magnitude of the force, and we have to give the direction of the force, that is x-axis here, as you can see here. I just go here, it's along the x-axis, right? So this is how we'll create the constraint and the load, right? So after that we need to create the material for the rack and pinion, right? So the material I have used for the rack and pinion are same here, okay? I have used the default material steel. So why default? Because if you just click on the empty space here while creating a new material, so these values are present by default, right? So it's the easiest one to use here. Fine. So I've used the same material steel for both rack and pinion. So I can go to properties. You see I've created one property for rack, right? P solid because I've meshed it using 3D elements, and material will be steel, right? And for pinion, again card image is P solid and material is same steel, right? So we have the meshed model, right? We have load steps, right? Constraints and force, and we have the materials and properties created. So can we proceed to the analysis? Not yet. So the thing is, since this is a non-linear contact analysis, right? Contact, we need to define contacts. So how to define contacts? So for that we can go to contact here. Yes, if you can see just beside the model. So you can just click contact and this browser will be there, right? So if you can't see this here, you can just go to view, right? Here beside it view, and you can go to browsers, then you can go to Hypermesh and there will be one contact option. You just have to tick it and it will come, right? So for creating the contact, so what we'll do is we'll basically use auto contact. So for that we'll just select this pinion and we'll select a rack, right, component, and we'll just right click and there will be auto contact option and you can just click auto contact and it will create the contact. So I'm not clicking auto contact because I already have contact created. If you can see here, right, I'll just increase, expand the dimension so we can see it clearly, right? So once you click auto contact, contact will be created like this, right? So in this, the type will be slide, right? So contact type is slide. So slave ID is the pinion and the master ID is the rack, right? So slave is basically this pinion, right? Because master is the one which is undergoing the force, undergoing the motion, right? Okay. Basically the driver and the driven kind of thing, right? So master is the rack and slave is the pinion, fine. And some other values I've used here is, so clearance I've given 0, like it's very close. Then discrete I've given surface to surface, right? And track is constantly, right? So if you want to see all these things in detail, you can just visit my website. I have given the detailed process and with what values to put in what fields, right? So you can just follow along that if you want. And if you have any doubt, you can just comment me there or comment on the YouTube video. I'll just respond, right? So once you do that, contact will be created. So you can see here the groups. This is basically the contact. contact and we can review the contact, and you can see there's a contact here, right? This is the rack, right? And here is the pinion, right? So this is how the contact is created, right? Okay. So we have the mesh model, we have the material, we have the property, we have the load step created, we have the contact created, right? So sorry, we have the load collectors created and we have the contacts, right? So next what we need to create is we need to create the load step, right? So non-linear, right? So since this is a non-linear contact analysis, we'll be creating a non-linear load step, right? So we'll just create a load step, okay, as you can see here. Okay, and analysis type we'll select as non-linear static, right? Next, we need to create the non-linear parameter, right? So for that, we need to create a load collector. So I have already created that. You can see here, NL param, right? So for this, I've used 0.1 in the DT field. If you see here, right? And then we need to create one more load collector, that is NL out. In that value, I have given as 2, right? For the int field. Okay, as you can see. And if you have just miss out on anything, if you have any doubt, you can just visit my website and check again, right? So for this load step, we need to use both these load collectors, right? Apart from the constraint and load applied, right? So under the SPC field, we'll place this constraint which we have created, right? Under the load field, we'll place the force which we have applied. Under the param field, we'll place an param, right? And under the NL out field, we'll place an NL out load collector, right? So this is all fine. So basically, we are all set to perform the non-linear contact analysis. So we'll just okay. So for performing the analysis, we just need to go to analysis, right? And we can just go to Optistruct here. If you can see Optistruct, we just click on Optistruct and we'll select export options to all, run options to analysis, and we'll just click on Optistruct to run the analysis, right? Just click Optistruct. Okay. Okay, so once you click on Optistruct, a pop-up window like this will open, right? Which you can see here. So this window shows you the progress of the job, right? So if you can see here the progress of the job, iteration 0, convergence 0, progress 100%. Okay, so we'll see what happens. And here there's a message log. The message will pop out, like if there's any problem in the run, or the run was successful, whatever it is. It will come here once the run is complete. So we'll just wait for this run to get completed and we'll see what happens. Fine. So we have message in the message log, messages for the job, analysis completed, right? And right. So there was no problem, analysis was successfully completed. So now we can basically go and view the results, right? And if you want to view the output file, you can just go to this view, click on the drop down adjacent to it, and there will be output file option. You can just click on that. So you can view the output file there. If you want to visualize the results, you can just click on this results button here, which I will click now, and we'll just visualize the results. if you click the results button, hyperview window like this will open, right, which you can see here. Okay, and I have everything here, right, the rack and pinion. You can see the displacement is plotted, right. You can just visualize the displacement. Okay, right. So this is the displacement, right. You can see the rack is displacing, and the top part of the pinion, the part very near to the center of the pinion, it's almost negligible displacement, since this is the place where we have constrained all the degrees of freedom, right. So, and the rack is free to move, so it's basically moving. So next, this is the displacement plot, right. So we can just go to element stresses here from the drop down. You can just click on apply, and you can see the element stresses, right. So the element stresses are like majority around the point where there is a contact, right. You can see, we'll just zoom in a bit. Okay, and you can just infer from the legend what is happening here. So we basically have something major going on here around, right. So it's all colorful here, and these are the dark blue region. That's very negligible stress compared to these regions, right. Okay, so basically this is how you determine the stress at contacts, and you perform non-linear contact analysis, right. So you can perform it in various parts which are under contact to determine if there's any failure in them based on their stress values, right. So okay, so this is all for this tutorial. Hope you liked the tutorial and you got to learn something new. So see you all in the next video. Keep learning, and please like, share and subscribe, and do visit my website too. Thank you.